started from the Newton's second law. We started complaining, oh, Newton's second law, it's all about vectors. It's tedious and boring to work with vectors. Let's try to simplify our life. Maybe we can get rid of vectors and introduce a different set of tools which can be used instead of vector quantities. Of course, we started switching to scalar quantities. And after some massaging of the Newton's second law, we ended up with the work kinetic energy principle. Since moving from here to there, we did not make any assumptions, pure calculus. As a result, this work kinetic energy principle is as universal as the Newton's second law. So pretty much in the energy approach, this is our mother lode. So we can solve any problems using that approach, just using work kinetic energy principle. So it is as powerful as Newton's second law. Right? Although it's not considered as some fundamental equation because we derived it from the Newton's second law. Newton's second law is the fundamental equation. Then, of course, kinetic energy, definition of work. In the most general case, of course, it's a F dot dl, but since most of the time our system is one-dimensional, so I reduced that integral to one-dimensional, F dx. Right? And if force is constant, of course, we can simplify this expression. And if the force is constant, of course, that can be easily transformed into this F times displacement times cosine of the angle, correct angle between these two vectors F and D. But if force is a function of x, right, so then instead of integration, we can just calculate area under the curve. If you plot F versus x, area under the curve, of course, it's the value of the integral between that initial and the final points. OK, so we will practice that. Then, at this point, we started looking, so maybe for some additional simplifications, right? So, and we noticed that there are some forces and work done by those forces is path independent. Wow, we can skip integrations. Instead of integrating every time, maybe we can introduce some function which can be some function like potential energy, right? So, and so we introduce it. For conservative forces, if force is conservative, then potential energy can be introduced. And in our cases, in our problems, we have only two conservative forces, gravitational and spring force. They're both conservative. We proved that gravitational force is conservative. I did not prove that spring force is conservative, but again, it can be done, but you have to do integration, actually. And corresponding potential energies, mgy and 1/2 kx squared x. It's a displacement from the equilibrium, right? Not just arbitrary position of, position of the object relative to some arbitrary origin. No, relative to the equilibrium. And then work done by the conservative force, we showed it is equal to the negative change in the potential energy. Great, so we introduce potential energy, and then immediately once you introduce that, and if there are no non-conservative forces in the system, work kinetic energy principle can be changed to the conservation of mechanical energy. Again, if you don't like this, you can go back and use work kinetic energy principle. It's, again, universal. But if you want to skip integrations, you can introduce potential energy and use conservation of mechanical energy if there are no losses, if there are no non-conservative forces. But if there is a non-conservative force or there are non-conservative forces, in that case, there will be all the time losses, work done by the non-conservative force. So there's like conservation of mechanical energy and then work done by those forces, which most of the time is negative. So this is losses. Your final will be equal initial minus that. OK, and the last item, essentially about the energy approach. We discussed a few cases that sometimes information about the work is not enough in order to distinguish different devices or efforts of different people, because sometimes you do exactly the same amount of work, but no, not consequences, but the results can be different, like I used example about work done by us. Also important, how fast that work is done, right? How fast the work is done. It's like if you take a cheap car, an expensive car, they all can do exactly the same amount of work accelerating from 0 to 60 miles per hour, right? But how fast that can be done, it's a big difference, and that's why one car is cost like 12 grams or 20, and the other one is 200 grams, right? Because one car can do that work in 26 seconds, the other one in 3 seconds, right? So of course, idea of power is very important. So we introduce two: average power. So you take the total amount of work done by a certain force and divide it by the time over which that work was done. And instantaneous, if force is changing from time, moment to moment, from point to point, right? So then if you take the force and dot it, scalar product, with the velocity vector, so that will be the value of the power at this particular moment of time. Maybe next moment of time, force will be larger, velocity will be different, and then of course the power will be different. So that's why it is called instantaneous power. But of course, if force is constant, this and this are going to give you exactly the same answer. We're going to look at one example. Okay, and then definition of scalar product. In my sections, I give a special even quiz dedicated to this scalar product because students refuse to remember how to find the correct angle. Right? So in order to find the correct angle for this dot product and in the future vector product, you need to position tails of both vectors at the same point. And angle, which is less than 180 degrees, is the correct angle. Right? Okay, so that's essentially the scope for the exam in my sections, but in your sections, I'm not exactly sure where your instructors are right now. Okay, so let's move with the problems then, start solving problems. The first one, I want to solve very simple about scalar product, and then, of course, work kinetic energy principle and so on. So the first one, that's just a scalar product. What if we have these two vectors? Vector A and vector B. All right. Actually, the numbers are given. So the value of this vector A, how should I write? Okay, let me write it like this. For the value, magnitude of vector B, I think is 2. Yeah. Whatever units, it doesn't matter which units. Scalar product doesn't care about the nature of vectors. If you tell it, okay, it's a vectors, okay, it will treat them as vectors. Units not important. And let's assume this angle is actually 60 degrees. Right. So in this case, what is a scalar product? Of course, it will be A dot B. So you need to take magnitude or absolute value of vector A. Over here, you must not show the vector sign. Now it's a magnitude, because very often I see students still try to show the vector sign. These are magnitudes. A times B and times cosine. Is that 60 degrees correct angle between these two vectors? Yeah, in this case, yeah, it's obviously correct because you see tails of both vectors at the same point, and this angle is less than 180 degrees. This angle, of course, is larger than 180 degrees. It's not the correct angle. We need to use that one. Right, so yeah, in this case, it's just 60 degrees, and we have what? 4 times 2. Cosine of 60 degrees, it's 1 over 2. I still remember it well. So we'll get 4. Now, what if we have this situation? What if this is vector B of the same value, and this is vector A, and the same 60 degrees angle? Vectors in absolute value the same. But now you see I position them like this. Okay, so again, it should be A dotted with B. It's a AB and cosine. And now, of course, the question, which angle is the correct angle? Which angle is the correct angle in this case? Okay. Well,
I think it's 30.
30? Of course, my angle looks like 90, but it's okay, guys. You remember again the major. Okay, I know because I keep bugging you in my sections, right? So you remember how to find the correct angle. Okay, we have here plenty of vectors. Let me grab a couple of them markers. The main idea, you need to position tails. It doesn't matter, for example, vectors like this, and you remember you can move any vector if you preserve its magnitude and direction to any point you want. You can take it home, you can take it anywhere, right? So as long as you preserve it, will be still the same vector. So in this case, you see we have a tail of the first vector here, tail of the second vector there. They are not at the same point. So we need to just grab one of these vectors, move it somewhere so that tails will be at the same point. Okay, let's do it. So in this case, I don't know which one. Let's move vector A, for example. I can grab this vector A and displace it and position it here. Right? It's still the same vector A. I just position it at a different spot, but again, it will be still the same vector, exactly the same vector. You remember properties of vectors. So I can position vector A over here. And now you see tails at the same point, and that angle less than 180 degrees. This angle is larger than 180 degrees, so it's not the correct one. So this is the angle theta, which must be used in this case, scalar product. And in a couple of weeks, we will introduce the vector product. Still the same rule will be used to find the correct angle for the vector product. And even sometimes physics major senior students still struggle with that. Yeah? Yeah, no, it will be just 120 without minus anything. It's essentially 180 minus 60, it will be 120. Right, so 120. Yes, okay. So in this case, let me even use different color. So it's 180 minus 60 degrees. It's at that angle. It's 120 degrees. So it's 4 times 2 times cosine of 120 degrees. Okay, it will be still, of course, an absolute value the same, but of course it will be negative. Cosine of this angle is negative, so it will be minus 4, whatever units, right? So it's just a mathematical tool which we just need to remember how to use. At this point, even don't try to find the meaning. It's just in order to explain what we observe around us, people introduce these tools like dot product or vector product later, or cross product. And again, in my sections, I gave a question. I mean, the quiz with plenty of, a few questions where students needed to find the correct angle. It's still, there are some issues, yeah.
The second one's right in this scenario, or is it two separate questions?
Two separate questions. Two separate questions, yeah. I just wanted to show that essentially it looks like the same, but I changed the direction of vector A. Oh, essentially I could have changed the direction of vector B, right? But the same, potato, potato. Okay, let me then, if it's confusing, let me put first bullet here and then second bullet there. So two different questions, unrelated. I just want to show sometimes this is the correct angle and sometimes it's not a correct angle. Okay, so and this is how to find the scalar product using this formula. It's just trivial. It's just components are given, multiply, add. All right, so we're not going to do that. Okay? Okay, good. And again, it's essentially it's alphabet. We're learning some simple, trivial things which should be in your blood already. Okay, not already, but in the process, right? So your blood should be contaminated with all these things, right? So when your boss will start talking to you about some work that needs to be done, that you can follow, right? So explanations. All right, so now the next one, you know what, let me just move on and then I will erase this. So second question, let's calculate the work done by the force which is not constant. If force is constant, yeah, we can use this, right? So, but if the force is not constant, essentially it's an integration or calculating area under the curve, right? So let's do it. Let's practice this. Okay, let me use a curve. Okay, so let me draw the picture. I mean, not the picture, the graph. So let's say we have force, units of newtons. I need both below and above. So let me, then this is x. I hope it's enough of length. Maybe I'll have to increase, we'll see. And let me put points. Up to 15, oh my God. So 2, 4, 6, 8, 10, 12, not enough. 12, all right, wait. 14, 16, and somewhere between them will be 15. Okay, so 2, 4, 6, 8, 10, 12, 14, 16. All right, and here, 400 newtons, of course, this will be half, and here will be minus 200 newtons. Okay, so this picture. Yeah. Okay, and now the graph. So from 0 to, this is the point 3. So let me, the graph goes straight up. So this is the midpoint between 2 and 4, it's a 3. Right. Maybe I can show in red, so it's a 3. Then it stays constant till 7. And then goes down to negative 200 at point 12. Somewhere here. And, okay, you know what? This line is too long for my hands. And then again stays constant for 2 meters and then goes down to 16. Wait, 15, sorry. So that's 15, and there's 16, next one. Whew. I think this is the graph, and this is x in meters. You know what? Yeah, let's do it step by step. Part A. So let's first discuss what is actually physically happens. It's a one-dimensional situation. Some object moves along x-axis. First force is positive. What does it mean, positive? In the positive x direction. Let's assume that this is our positive x direction. So it means that force, first you increase the force from 0, first there's nothing, then you increase force over 3 meters to the maximum, and then you push that with that force for whatever, 4 meters, and then you start reducing that force. So reducing that force till this point, now force is 0. It doesn't mean that the object stops. It might still be moving, most likely be moving, right? So, and then what happens after that? You change direction of the force. Now you see the force is negative. Negative force, negative vector, it means that now object is still moving forward, but now you apply force in the opposite direction, trying to slow it down, essentially. And then you slow it down from 10 to 5, or to 15 for 5 seconds. So first you increase that slowing down force, then you keep it constant, and then you start again, start reducing that force. Right. So it's still motion of the car in the same direction, but the value of the force keeps changing from point to point. Right. So force is not constant. So if we want to find work, this cannot be used because it's not designed for that, not derived for that. Okay. So now let's calculate first work done by this force between 0 and 10, and then from between 0 and 15 over the whole path. Right, work done by this force. So now part A, so work done by F in first between 0 and 10 meters. Oh, let me call it W010. How did I label it? Ah, okay. Let me label it like this, W0 to 10. Okay. Of course, strictly speaking, it's an integral of f dx between 0 and 10 meters. But again, yeah, Yeah, since most of you didn't take calculus 2, so you're not familiar with integration, so we skip integration, and every time we just use geometrical interpretation of integration. It's just an area under the curve, right? So in this case, it's the area of which figure? Let me just label the points on the graph. Let's call it point, maybe let me follow mine. Okay, this is 0. Wait, not 0. O, A, B, C, D, E, F. So let me just label all the corners, right? So in this case, area which we need to find, it's this area. That area equals to the work done by this force as the object moves for between 0 and 10 points, 0 meters and 10 meters. So area of that, it's essentially trapezoid. Right, it's trapezoid. Area of that figure, O, A, B, C, trapezoid. Right. Of course, you all know how to find the area of trapezoid. It's a 1/2. This base plus that base and multiply by the height. Right. Yeah. So it will be, let me write below, 1/2 base 1 plus base 2 and times height. Right. Okay, so let's just plug numbers. So it will be 1/2. This base, it's a 7 minus 3, 4 meters. Then this base, 10 minus 0, 0. I mean 10, 10 meters. And times height, height is 400 newtons. Right. So as a result, 14, 7, 2800, right? Yeah, 2800 joules. Units of work or energy, joules, right? If you forgot, at least write down, so what you see in the formula, it's a newtons times meters. It will be also absolutely correct. I would never be able to tell you, or your instructor would never be able to tell you that you are wrong. It's right. You just refuse to use simplifications. Joules was introduced to make your life a little bit easier, so that you wouldn't be pronouncing that every time. Joules times, newtons times meters, and joules. Right. Okay, so now let's calculate the work done by this force over the whole, over the whole distance covered by the. I will pick it up later. So work between 0 and 15. Right. Okay, so now we need to calculate the whole area. And I'm not going to calculate again this area because we already calculated, right? So it will be work done between 0 and 10 plus area under the curve of CDEF. CDEF. Right. So the same area of a trapezoid. So it will be 2800 joules and plus 1/2. Bases, here it's 14 minus 12, 2. This base, 15 minus 10, it's 5. And times height. Height is negative, minus 200. Okay, probably I should have used this dash line to show that this is the level of this. So negative 200 newtons. Of course, never skip this minus because this minus gives us a negative area. Right. So, 7. Okay, now it's getting more complicated. 3.5. I'm getting 700, negative 700, right? Yeah, negative 700, yeah. So it will be equal to 2,100 joules. Right. Again, it can be easily integrate it if you are familiar with integration, because these curves are just a straight lines, right? So you can easily write the function and integrate it. Yeah.
Can you give us an example of that? Like, could you write the function that we're supposed to integrate?
Okay. So, for example, the easiest, this is the straight line. So the function is what? F equals to 400. It's your function. Actually, in this case, it's a constant. You can immediately apply even that for that particular range. But this, okay, let's just use this from 0 to 3. So function as a function of x, it will be what? It goes through the origin, so intercept will be 0. And the slope of this, it's 400 divided by 3. Okay, let me just write 400 divided by 3 times x. So this is the function describing this straight line.
And from 0 to 3.
Yeah, and of course 0 to 3. And then the work done over that range from 0 to 3, it will be integral of this 400 over 3x dx from 0 to 3. Right. So
Would you
yeah,
be
you
allowed
go.
to do that? Would you be allowed to do that on the exam?
You must not even ask. If you know, if you're familiar with integration, do it. I would be ecstatic if I see that you actually use integrals to calculate the work. But this is easier because all the functions are straight lines. It's easier to just area, calculate the area. Right. Actually, this is also calculation of the area, but in a pure mathematical way. Right. Yeah. Of course, it will be x squared over 2 times this factor, and then plug upper and lower limits. Right? Yeah, so it can be done. From the point of view of calculus integration, it's a banal integral. It's a banal situation. Right? Of course, here slope will be negative. Right, so. Good? Remember, again, we're not going to discuss something radically new or radically complicated. No. At least my policy in my section, if you know by yourself how to solve problems from your homework and what we've discussed in the class, you should be able to ace the exam. Because every time when I create the exam, I remember what was discussed and what was covered. Right? Just different slightly situations so that you would apply the same ideas to slightly different situations. All right. Okay, so now let's push the piano down the hill. In the class, I think we did it up the hill, and now let's. And I think in the class it was force applied horizontally. Now the force is along the incline. Okay, so let's just again practice how to find the correct angles between the force and the displacement. Right? Because again, based on the quiz results, still plenty of work needs to be done. Right? And again, it's not the most complicated rule. Right? So how to find the correct angle. And you know what? I'm just trying to estimate the amount of space. You know, let me start erasing this. Because over here we will have to find plenty of works. And I'm afraid that I will not have enough space over there. So this will be number 3. So again, we're not pushing the piano up the incline, but it's like when you already arrive to a new place where you want to live and you want to gently move the piano down from the track along the inclined plane. All right, so this situation. So we have a piano. Okay, let me write piano on an incline. So, you know, let me start with a picture. So, okay, let me move slightly lower. Yeah, on this slope it will be difficult to move the piano down. But it's just an example, so not real situation. Okay, I will just draw a box. So this is our piano. All right, mass of the piano, let me write 380 kilograms. Okay, yeah, heavy. Then length of the incline is given, 3.9 meters. I'm not going to draw it over there because we're going to have plenty of information on the picture, and I will just write over here. So it's 3.9 meters. Then angle of inclination, theta, 27 degrees. When I was a student, my professors used all the time only nice angles, 0, 30, 45, 60, 90, and here everything, 27, 32, 35.6. Right? Okay. So yeah, we're moving from the top to the bottom. So we're carefully unloading it from some height area. Right? So it means that displacement, they use L. You know what? Let me change this L to D, because we usually use D symbol for the displacement, right? So let's just stick to that notation, D, displacement. And let me show immediately on the picture this displacement. This is our displacement D. Okay, great. Then, additional piece of information, as I kept bugging in my section, practically, how do we usually unload things or lift things up? Every time without acceleration, with constant velocity. We usually don't, because if you start experiencing or try to provide acceleration, then it's much more efforts you have to apply, right? So of course, we usually move things with constant speed. So we're going to make that assumption. Assume velocity equals constant. That's my constant, const, right? The value of that constant is not important, right? As long as it is constant. Okay, I think that's what is given. Yeah, nothing else. You know what? Let me show the person over here. No, it's a person pushing, not pushing, applying force, right, so that the piano would move with a constant velocity. Yeah?
What does that say next to the 380?
Kilograms, kg. Yeah, my students from my section, they're already familiar with my handwriting. Yeah. Okay, let me introduce coordinate system, because we will still need to find some forces, so we will have to apply some Newton's second law very quickly in order to then later to find our words. So let me introduce coordinate system, and of course I will introduce the most convenient, y, and this will be my x-axis. Right. And so again, the question will be, we will have to find the force that the guy has to apply to move this with constant velocity, and then we'll have to find the work done by that guy, work done by the gravitational force, work done by the normal force, work done by all possible forces, right? Okay. Actually, can you tell me immediately what will be the net work? Can you see the future, the final point? We will have to find eventually the net work. Can you tell me maybe immediately what's the total work? Maybe you can see the future. Future teller. No? No? Zero? The guy will be sweating like hell. No, you're absolutely correct, actually. You're absolutely correct. Yeah, you absolutely. I was just trying to make a joke. Of course, he's absolutely correct. Why 0? Of course, we will show it. And 0, the easiest way to see it, look at the work kinetic energy principle. What can you say about kinetic energy of the piano at the very beginning and at the very end? No, not change will be 0, but the kinetic energy will be the same, because we move with an object with a constant velocity. So at this point, let's say it's 3 meters, oh no, 3 meters per second is too fast, or whatever, right? So 50 centimeters per second, right? And exactly the same will be here. And then, of course, 1/2 mv squared, of course, is going to be, and of course, piano is not losing masses as you move it. Right. Yeah, so of course, kinetic energy stays the same, so delta K will be different. Oh, 0 will be 0, and it means that the work will be 0. So it's immediately, whenever you see a system moving with constant speed, you can tell immediately, net work is 0. Doesn't mean that all works equal 0. Net work, total work done by all the forces will be 0. Right. Okay, so now actually let's find all the works done by all forces. Free body diagram. Still, we need to draw them. We try to move away from vectors, but still, as a preliminary steps, you need to discuss forces. Okay, you all know it was in the previous exam. So force of gravity straight down, mg. Then a normal force perpendicular to the surface, Fn. Then force that guy applies up the hill, right? So we assume it applies the force up the hill, not at some strange angle, right? So this will be force that, how did I label it? Fp probably. Ah, no, just F. Okay, why not? So this is the force that the person applies. And I think we're going to assume that there is no friction. Yeah, ignore friction. Let's ignore friction. No friction. I should have added this. All right, so no friction. It's a nice statement, right? So easier. Right. Actually, yeah, sliding the piano on the icy surface is not fun. No friction. All right. Okay. So, and yeah, that's it. Nothing else. Yeah. Okay. So now, first in part A, we need to find the force that the guy has to apply. So part A. What's the value that a person has to apply? So again, Newton's second law, in both directions, y and x direction must be applied in order to answer that question. Okay, sum of the forces in the y direction equals to mass times acceleration in the y direction. Sum of the forces in the x direction, mass times acceleration in the x direction. Do we need equation in the y direction, actually, from the practical point of view? Since friction is not there, yeah, we can find that the normal force will be equal to the component of the gravitational force, right? So, but since friction is not there, that kind of dead-end direction. But anyway, so let me. Acceleration in the y direction is 0. Acceleration in the x direction also 0, because we are moving the piano with a constant speed. Okay, so then you remember the composition of the mg, of the gravitational force. This will be the y component of the gravitational force. This will be the x component, right? And you remember the geometry we discussed a few times in our classes. This angle actually equals to that angle. I'm not going to, again, repeat exactly the same procedure. Right. You remember. This angle will be 90 minus theta, and then this and that, they complement each other to 90 degrees, so this angle must be theta. Okay. We've done it as a preparation for the second midterm exam. Okay, so then, as a result, this component, it will be mg times cosine theta, because this is the side adjacent to that angle, and of course, opposite side will be sine. So this will be mg sine theta. Okay, so since there's no acceleration in the y direction, so this force must be equal to that force in absolute value. But of course, they're in the opposite direction. So it's from the equation, from the y equation, we are getting that Fn equals to mg cosine theta. But again, it's a dead end. We don't need it because friction force is not in the game. So from this equation, what are we getting? this component of the gravitational force in the positive x direction, so it goes into equation with plus. Again, you had a problem almost like this in your second midterm exam. So it will be mg sine theta. Then force that person applies up the incline, it's the negative x direction, so it goes into the equation with minus f. And it is equal to 0 because acceleration is 0. Right, so there are only two forces. And immediately from here, that force that the person must apply must be equal to the component of the gravitational force. Right? So F equals to mg sine theta. Okay, you can plug numbers. All the numbers are given. I will write down immediately the answer. 1691 newtons. 1,691 newtons. Of course, it can be rounded to 1,700 newtons. Wait, that's the ugly newtons. Right. So that's the value, the force that person must apply in order to move the piano with the constant speed. Okay, this is still we haven't started solving the problem. We just it's a preparation. So, and now let's start finding all the force. Works done by all forces. So that was part A. Now part B, let's start finding works. First, work done by the person. Work done by this force F. Force is constant. So now we don't need to do any of those funky moves, right? Although if you want, you can do that. We can immediately apply F dot D. F dot displacement. So F dotted with displacement, or scalar product between F and D. Okay. Again, dot product, magnitude times cosine of the angle between them. So it's F, D, and cosine. As I said, sometimes students still keep writing over here a vector sign. Now it's not a vector, it's a magnitude of that vector. Right. Again, strictly speaking, it's kind of a mistake, but of course I would never subtract any points for that. I just usually cross that when I grade the exam paper or quizzes, but usually don't subtract. When I grade exam papers or homeworks of seniors, physics majors, of course I usually tougher in that sense. Okay, angle. Now, can you see the angle? That's, you see, on purpose I stopped cosine, and now I didn't write the value of that angle. Huh? While you're thinking, let me check. Yeah, good. Picture. You everything all is on. Huh? Yeah. Yeah, every time there is an angle, unless if there is no displacement, then of course it would be impossible to define the angle. But in this case, there is an angle. Look at the picture. What's the direction? I know, I see it. All right, so what's the direction of the force? Up. Okay, so it's not, yeah, it's negative. Yeah, so but anyway, that way. What's the direction of displacement? What's the angle between them? It's banal. It's a banal situation. Of course, you all know how to find that. I just I don't understand why you refuse to see it, because it's here in front. That's why I keep drawing, and I keep asking students, guys, draw, because it's supposed to help. Right? Even if you're quite experienced, you still can make stupid or silly mistakes if you don't see a situation in front of your eyes. Right? Yeah. Of course, everyone sees 180 degrees, of course. Right? So 180 degrees. And so the work will be, of course, negative. And of course, because that's what essentially, that's his job, right? So piano wants to roll down, and you try to stop it, prevent it. So you do negative work, right? You're sort of trying to dump energy out of the system, right? So numbers are given. We found this displacement is 3.9, angle you have, so I will write immediately the answer. Negative, okay, I will use all six, I mean all sig figs. Okay, 4 sig figs. Of course, you can round it to 6,600, but I will keep it. I will keep them all digits. Great. So now, next work which we need to discuss, work done by the gravitational force. A, B, C, work done by the force of gravity. Yeah.
I just have a question.
Mm-hmm.
So you found that the force that the person's putting on the box is the same.
Piano. Yeah, box. Yeah.
Is the same as the x component.
Of course, it must be. It must be because we want to slide it without acceleration. Because if it starts accelerating, then it's much more difficult to catch it right and slide it right. Of course,
And
yeah.
So the f is this one.
Yeah, equals to the value of the x component of the gravitational force. Yeah. Every time, if you know there is no acceleration, then forces must balance each other out. Yeah.
So why don't we use the y component of that equation?
As I said at the very beginning when we started writing down, and I asked, do we need that? No, it's a dead end. It's not that we need it. If we had a friction force, then of course we would need this value in order to find the value of the friction force. So this is kind of not needed, right? But since we started writing Newton's second law, so I decided to apply in both directions, right? But of course in this case it doesn't give us anything. Yeah, force of gravity. Now work done by the force of gravity. The same story. It's a constant force, so we can use just a dot product mg dotted with d. Again, magnitude of the force, magnitude of the displacement, and cosine of the angle. Now, which angle do we have to use? Which angle do we have to use now? Linda, do you see? You already started analyzing. Do you see the angle? At least maybe you can tell me verbally which angle is the correct angle, and then we'll start finding it. Again, you need to see what's the direction of this vector, what's the direction of that vector. You see it? mg, you see it's a red, this straight down. Then displacement, we're moving the piano from this point to that point, so displacement is along the incline. So these are our two vectors. So, and the tails of both vectors are at the same point. Yeah. Okay, I assume that this is the yeah, these are tails, right? Yeah. So this is the correct angle, right? And it's not theta. Everyone sees that. So let's find that angle. So essentially, we need to find. Let me show it this. As alpha for now. So in order to find that angle, actually trivial, everyone sees that. Do you see the angle, the value of that angle? Okay, I know you see. Can you see, do you see that the value of this angle? You do know. Look, this is perpendicular to the inclined plane. So this angle is 90 degrees. And this angle is theta. So the whole angle is 90 degrees, and this is theta. Then this angle is 90 minus theta. 90 minus theta, right? So let me erase it and write 90 minus theta. Play with geometry, right? So it looks like in high school, I remember my high school, and I remember we had some crazy configurations of all the triangles, and you can spend hours figuring out which angle must be used in order to find this or that side. Yeah.
I think on the quiz you gave recently, the
It was different plus it come on different configuration, different situation, right? So it's not that there is a certain angle which is everywhere. No, it depends on the direction of the vectors. In this case, mg that way, displacement that way. In that situation, okay, I don't remember exactly the geometry, but in that case, yes, it was 90 plus theta. Again, it's a different case, different situation. Okay, make sense? See that? Great. Right. So it's okay. Let me write 90 minus theta. Of course, you can subtract. Right. So it will be whatever 63 degrees, right? Huh? No, I think 63, right? Because 90 degrees, not 100 degrees, right? Okay. Again, all the numbers are given, so you can calculate. I will write the answer immediately. Okay, so got it. So I confused myself, right? So I was just looking, this is the force and this is the work done by the force. Okay, now I clear it for myself. Get confused. Okay, so A, B, C, and yeah, I wanted to write the answer. It's plus positive 6595 joules. 6,900. 595. Actually, I could have written even without calculation or looking at my notes. All right. So the last force, normal force, A, B, C, D, work done by the normal force. Okay. So normal force times displacement times cosine of the angle between these two forces, right? So what's the angle now?
90.
You see it now? Okay, now it's better. Right, so yeah, you're getting the idea, right? So yeah, of course, 90 degrees. Normal force, displacement, they're perpendicular to each other. So 90 degrees. Cosine of 90 degrees is 0. So any work done by any force which is perpendicular to the displacement, 0. It's basically, in this case, it's called force of constraints. Its job just to guarantee that the object moves along the incline, along that trajectory. And it cannot change the state of the motion. It just gives us the path. Right, so done. And now let's calculate the network. Network. So A, B, C, D, E. Work net. Okay, so all of this must be added. All works done by all forces. So work done by F plus work done by gravitational force and plus work done by the normal force. Normal force is 0. And this, of course, must be the same in absolute value and opposite in the sign, because we know velocity is constant, so the net work must be 0. That's why I told you I could have written this number without even looking at my notes, because if we have here negative, this must be positive, right? Because I know the net force, new net force must be equal to 0. Okay, 0 joules, as it should be. As it should be, since V equals constant. Sometimes I envy when I watch videos of classes from MIT when they can move the blackboard up and down, so I don't have to almost kneel in front of the whiteboard to write something. Right. Okay, typical problem which is offered quite often on the exam, where you need to just find works done by all the forces acting on the system.
On an exam, would the force of the person be given, or would
Come on, it depends, right? So it's possible that velocity is constant, and you need to very quickly use your past knowledge, right, and find it, or it can be given, right? So it depends on the situation, of course. I cannot predict that. Good? Following? Okay, good, 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 good. Yeah? Feeling better? Again, I even struggle with some physics majors about that because they also refuse to follow the rule. All right, okay, so the next one. So we practice finding the work using this idea, this idea. Now let's move into the conservation of mechanical energy problems. Right. So let me start erasing this part. This eraser is getting dirtier. Okay, so now, you know what? Yeah, let's do the spring thing. All right. So it will be problem number 4. I prepared about 7 or 8 problems. We'll see how it goes. So physical situation. I don't have a spring. I need to get somehow which can stand vertically. So spring is attached to the, I know, some surface, to the table. Right. So then, and of course it's not falling, just stays in the vertical direction. It can be easily achieved, right? So then you take some object, compress the spring with that object by some distance, then release it, and of course the object will fly. So first in part A, we need to find velocity of the object when it's ready to fly away from the spring, when the spring gets to the relaxed length, right? So, and the object will start flying independently. So then we need to find that velocity, and then we need to find how high that object would go. Right? So two parts. Okay, so that's the physical situation, and now let me draw. Again, I like drawing because it helps, right? So to see the physical situation, and then see what needs to be done. So let me first title it like a, what is that? Table is compressed down. Actually, I didn't draw. Yeah, ball. Yeah, ball / spring. Right. Okay. So the first situation. Okay, let's assume that this is our floor. Right. First situation, when the spring is compressed. And the ball is on top. Right. So spring constant K. I think K is given. Yeah. K is spring constant. 875 newtons per meters. It's quite a stiff spring. You remember in your lab, which you did about you measured, it was like you had 10, 20, and 30 or 40, I don't remember, newtons per meters, right? I think green was the stiffest, and it was only 30 or 40, and this is 875, right? So it's quite burly spring. Okay, then compressed by a certain distance. Okay, so now let me draw the second situation when the spring gets relaxed. So let's say this is our relaxed spring. So this will be our first level. This will be our second level, where the ball is ready to fly independently. You know what, probably I should define position of the ball, not the spring. Right, so position of the ball. So this will be the second level. So let me write that this is level number 1. This will be level number 2. So at this level number 2, of course, velocity will be up. which we need to find. Let me label it V2, and that's our first question. Mass of the ball is m. Right. And then, okay, let me draw all. So for part B, the ball will fly. So the spring will be still here, but the ball will reach the maximum height. Right. So again, this is m, and this will be level number 3. Okay. So what else is given? Mass of the ball is given. Mass is 380 grams, so it's a 0.380 kilograms. Compression is also given. Let me write down compression. X equals to 16 centimeters. It's a 0.16 meters. 16 centimeters, that's spring. Wow. You need to apply tons of force in order to compress that spring by 16 centimeters. So let me write, it's a compression. Spring compression. So essentially, it's at this distance. Let me use different colors. So it's at this distance between level 2 and level 1. This is the x. Relaxed level, compressed level. So that's the level of compression of the spring. Something is not clear? Okay, you can use no. X in when you deal with spring, most of the time people measure that. Okay, in this formula, which we'll have to use spring potential energy, that x in this formula, it's a displacement of the object from the equilibrium position of the spring. So here, equilibrium position, maybe I can write it. So this is equilibrium, spring equilibrium. So every time x is measured from this level, by definition. Of course, like in your lab, which you did 2 weeks ago, you measured it from almost from the level of the floor, because that's where the motion sensor was, right? So, but then you will have to adjust it and find the amplitude of the oscillations from the equilibrium. You were supposed to find equilibrium level and then amplitude from the equilibrium. So you were adjusting those values of x in that particular experiment. Yeah, every time x, this x is from the compression of the spring or stretching of the spring. So where was something else? No, everything is given. All right, I think let me check one more time. Okay, so let's find that velocity. Part A, let me write it here. So part A, we need to find velocity of the ball at the second level. Okay, so let's start analyzing the situation with the forces. Which forces acts on the ball? Which forces act on the ball? Gravity first, right? Obviously. Conservative force. Work done by that force is path independent, blah, 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 blah. It's a conservative. So we can introduce potential energy, mgy. All right, so it will be the first potential energy. Whenever we introduce gravitational potential energy, we need to show what? The level where the value of the potential energy is 0. You can use any level as the reference level, but you need to show it on your picture so that you know if the object above that level, potential energy is positive. If the object below that level, potential energy is negative, gravitational potential energy. Okay, so it's your call where to position it. So there's no right or wrong, right? So I think in my notes I use level 2, yeah, this level. So I'm going to use this level as the level where gravitational potential energy equals 0. It's my reference level. Level. It means that if the object above potential energy is positive and it is equal to mg times this h. If it's below, it's negative immediately. Put minus mg and h. Distance between your level and the reference level. again, you can position the reference level anywhere you want. And it's very important, even like right now we're covering Lagrangian formalism in classical mechanics. And in order to find the value, correct value of the potential energy, every time I force students, show the level, show the reference level, so that you wouldn't lose the minuses or pluses, whatever. So it's very important, reference level. Okay, so then spring force, also conservative. And if we neglect air resistance, there is nothing else acting on the system. So only conservative forces acting on the system. So as a result, instead of using this, we can jump immediately to this level and use conservation of mechanical energy. But if you have something really against this conservation of mechanical energy, go back and apply work kinetic energy principle. It's universal. You can solve any problem using that principle. But in that case, you will have to calculate work done by all these spring force, gravitational force, and in spring force, you will have to integrate. Right. Yes. So it's just easier. So every time we move from here to something else in an attempt to make our life a little bit easier. That's the only reason. Yeah.
Is there a particular reason why you chose 2 as the reference level?
No, you can use this level as a reference level, and your answer will be exactly the same as mine if you do everything correctly. You can use this level as your reference level. It will be also correct, but then potential energy, gravitational potential energy, will be negative at all the points. Right. For my level, when the object is here, potential energy will be negative. When the object will be there, potential energy will be positive. Right. Again, I'm not claiming it's the only. You can use any reference level. I just followed my notes. I don't remember why I picked that level several years ago when I was preparing that. Right. Plus, probably because this is the spring equilibrium, this is essentially a reference level for the gravitational spring potential energy. Right. But again, it's not much of a simplification of solution. I don't remember exactly why. Right. Again, any level can be used. Right. Okay, so yeah, I think I justified that we can use conservation of mechanical energy. So let me write. So conservation of mechanical energy. So it means that you can compare energies at any 2 points. Any. Since we have some information at the point level 1, and since we want to find something at the level 2, so it makes sense to compare energies at those 2 points and find what needs to be found, if it's enough, right, information. So I can write, so E2 equals to E1, so beginning of the solution. So now we need to start diving until we start seeing all the quantities which we need to find and which are given. Exactly the same thing we're going, okay, very similar things we're going to do in physics too, when we're going to, again, develop an energy approach to solve problems about electrical fields and electric forces. Right? Very similar. Okay, so, but now we have 2 potential energies. One kinetic, because there is one object. One object, one kinetic energy. There are 2 conservative forces, 2 potential energies. So let me write them all. So K, should I start on which side I wrote? Okay, let's use K1 first. Okay, in mine, it doesn't matter. So let me write K1. K1 plus U gravitational 1 plus U spring 1 equals to total mechanical energy at the level 1. Then the same things. I'm just writing all possible, and after that I will start removing everything which is 0. K2 plus U gravitational 2 plus U spring 2. Right. And let me remind you, so gravitational potential energy, it's mgy. Spring potential energy, it's 1 over 2 kx squared. Okay, so let's start removing things. Initial kinetic energy. You don't know. Imagine spring. You take your ball, you compress the spring, and then you release it. So what's the initial velocity of the object just when you release the ball? Of course, 0. Of course, everyone knows. Of course, it starts from rest. Of course, we're talking about banal stuff, right? So of course, you all know this. So 0 because it starts from rest. Right. Everyone sees that, right? Okay, great. Then gravitational potential energy is not 0 because it's below the reference level, so it will be actually negative. Then spring potential energy also not 0 because the spring is compressed at this moment, right? So it's also not 0. Final kinetic energy, it's a level 2. It's not 0. It's our unknown is over there. Then gravitational potential energy. Okay, I'm just trying to remove all the quantities which are zeros, equals to 0. Gravitational potential energy at level 2. 0. It's a reference level. Reference level. Right. And spring potential energy, Ivan?
0.
The spring is relaxed right now, right? So the object is ready to lift, so the spring is not applying any force. Now it's done. Its job is done, right? So spring 0, now it's relaxed. Nothing else is 0. So we have 2 terms, non-zero terms over here and 1 non-zero term over there. Okay, so now let's write explicitly each of these terms. Gravitational. Negative, right? I forgot who asked. I think you asked if we change the reference level, right? So, okay, reference level here, our object below, so potential energy is negative. So it's a minus mg. And which quantity do we have to use in order to show that h, by how much the ball is below the reference level?
The displacement of the spring.
Yeah, it's a displacement of the spring. It's x. It's our x. So in this case, the same quantity is used in the expression for the gravitational potential energy. Just it happens. Right. So mg x. Right. Then spring potential energy. Okay, it's 1 over 2. Spring potential energy cannot be negative. It's only positive. Right. So k, and of course x squared because we actually have compression given. So nothing hidden over there. And it is equal to 1 over 2 mv2 squared. Okay. And how many unknowns? Again, every time we wrote down the equation, now we need to estimate, do we have enough equations in order to solve the problem? If we have 1 unknown, 1 equation, great. If you have 2 unknowns, 1 equation, okay, yeah. Right. So given, yeah, obviously given v2 unknown, right? So yeah, 1 equation, 1 unknown is a trivial things. At this point, physics is over. Now we just need to solve it for v2. M cannot be cancelled. Of course, you can divide the whole equation by m, so and m will appear over there. So let me do it. So let me multiply the whole equation by 2 and divide it by m. Yeah.
Where did you get the 1/2 mv squared?
No, it's correct.
No, yeah, is that k2?
Yeah, it's k2. This is 0. This is 0. I started doubting. I thought I made some boo-boo. No, it's a kinetic energy at the level 2.
Yeah.
Yeah.
And so
It's flying.
how is the x squared the velocity v2 squared? Because isn't it?
Okay,
How did you get 1/2 mv squared?
because it's kinetic energy. Kinetic energy, by definition, when we derived this work, kinetic energy principle, it appeared naturally, kinetic energy. So this construction, 1 over 2 mv squared, appeared naturally in the derivation. So we decided, okay, let's call it kinetic energy. Right. So this is essentially by definition. Right. It's not just we decided, oh, let's call 1 over 2 mv squared. It's just during the derivation, transition from this point to this point, it appears naturally. Yeah.
So the first part of the equation, negative mgx, is that just adding on the fact that there is gravity?
Rule is very simple. Once you pick your reference level, that level can be anywhere you want. There is no such thing as right or wrong level, right? All right, so you can position it here, you can position it here, you can position it there, you can position it anywhere you want. I just decided. So, and now once you pick that level, so if your object below that level, its potential energy is negative. If it's above that level, potential energy is positive. And every time, mgh from the level. H from the level, mgh. Rule is very simple, right? And it doesn't matter where is your actual origin of your x or y coordinate system. Potential energy doesn't give a damn about where is your origin. It just wants to know, is this your reference level? mgh positive, minus mgh, right? Yeah, yeah.
Is the spring always positive?
Yeah, all the time.
Okay.
And plus, this spring constant all the time positive. In this course, we sort of showed it conceptually, right? But in classical mechanics, it can be shown theoretically. It's positive all the time because it's a second derivative of the potential energy of the minimum point, so it's a positive all the time only. Right? Okay, so multiplying the whole thing by 2 and dividing by m so that I can free my unknown from any constant factor. Right? So it means this will be multiplied by 2 divided by m, 2m, and of course here 2 divided by m. And let me write v squared first, and then the rest will be on the right-hand side. So it will be v2 squared equals 2. Okay, let me write positive term first. It will be 2 will disappear. It will be k over m x squared. It's this term first I wrote. 2 over here, 2 over there, they cancel each other. Then minus m will disappear, and we will have 2g x, right? So m gets canceled with that 2gx, yeah. And that's it, and that's it, right? And now, of course, I will do a whiteboard magic. I will just remove this factor of 2, and I mean not factor, power, and put a square root sign. White magic, not black magic. Right? So let me check, make sure that. Actually, I factor out x over here, but you can do it. So k over mx squared minus 2g. Yeah. So I ended up, of course, at the right place. Okay, you can plug numbers. Everything in terms of newtons, kilograms, meters, everything is fine. So if you plug, you will end up with 7.5 meters per second. .5 meters per second, it's already a reasonable speed, right? So now, part B, let me create a new column. We need to find this height from the original level, between the level 1 and level 3. Again, this is the maximum point. So ball flies up, stops for a moment. So pretty much it's that. So we need to find this. No, it's this. Wait. So which way I label it? Don't remember. Or let me call it x3. Why not? So from this level to the point 3, right, x3. Okay, so it's up to you how to solve it. In my notes, I decided to find this distance between level 2 and level 3. Since we already explored level 1, now I decided to use level 2 and level 3 in order to compare energies. Right? Again, if you use level 1 and level 3, it will be also as simple. Right? So, I decided to use that. So we need to find now part B. Find x3. So see the figure. Right? You see that between level 1 and 3. So, and I will compare energies at level 2 and level 3. Again, if you use level 1 and level 3, it will be as good. Right? I decided to use this. Yeah, 2 and 3. So the same I will do it K2 plus U gravitational 2 plus U spring 2 equals to K3 plus U G3 plus U spring 3. Again, I'm writing everything, but of course, during the actual solution, of course, if you know it's 0, you can skip something, right? So because obviously, which potential energy is absolutely useless in this expression? Which potential energy?
The one all the way at the top.
No. Actually, there are two, only gravitational and spring. So which are over here all the time 0? At level 2, spring is relaxed. The ball is leaving. And at level 3, of course, the ball is somewhere at the top already, and the spring is still relaxed. So pretty much now, over this period of time, spring is not in the game. Right? So this and this will be immediately 0. Right? You could have skipped. I could have skipped it. Right? But I just wanted to write everything and discuss everything. Right? So of course, the spring is out of the game right now. So then, kinetic energy is not 0 at level 2. We just discussed all this. Gravitational is 0. It's our reference level, right? Yeah. This is the reference level, 0. And final kinetic energy. You wanted to answer the previous question. Now I'm giving you a chance to answer. Final kinetic energy. It stops for a moment. Again, it's a maximum point. Of course, it's 0. Right, so let me dump it this way, 0, because it stops. It's a maximum point. Stops for a moment. Right. OK. Only one term on one side and the other term on the other side. Great. I like the problems like this. So it will be 1 over 2 mv2 squared equals to gravitational. OK. You were asking about potential energy. Now, potential energy at level 3, is it positive or negative? Picture.
Well, it has potential energy.
No, it has potential energy.
It stopped at 3?
Yeah, I'm talking about gravitational potential energy, not kinetic. Kinetic energy we already ditched, right? So you see it's 0.
Positive.
Yeah, positive, because it's above the reference level. So it's, again, positive mg and times this distance, which is, let me call it h. Yeah. So let me introduce this and call it h. Again, it's not what we want to find, but it's a part of what we want to find. So it will be, again, emphasize, let me write positive mg and times h. Yeah. Mass distraction, right? You remember that, right? M and M can be cancelled, right? And we're getting that h, right? H equals to v. G goes over there. Oh, such a strange expression. No. Yeah, down. V2 squared over 2 times g. We square it over 2g. Yeah, it looks good. First, I thought it should go to the numerator. It looks so weird, so strange. OK, v2 is found in the previous part. Plug it. G, we also know. Right, so if you plug numbers. Actually, over here, it's 7.47. But again, if you use the rounded number, not a big deal. So the answer will be 2.84 meters. And the final result, what do we have to do with this number?
You add it to the
Yeah,
x value.
yeah. So now we just need to add x to this h. So in order to find x3, right? So I just split into 2 parts. So now x3 will equals to h plus x. So 2.84 plus, what's the x? 0.16 meters. So it will be, oh, nice numbers. Is it 3? Yeah. Right. problems like this, some of the easiest problems in this course, right? And again, in physics 2, when we're going to develop, again, energy approach to solve problems about electrical systems, again, students do usually the best. Right? So just compare energies. Again, the problem with the work is just finding this damn angle. Right? So that's the problem. Right? And again, it's not that rule is not that complicated. Right? Just a little bit of practice, and you should be able to do it easily. It's all about practice. Right. So now 1.5 hours. Good. Now, since some of you might feel tired, right? So, and you want to go, let's just solve one problem, because I want to continue playing with energy approach. But let me solve one problem about power, so that if somebody decides to go, so that we can practice at least idea of power. And then I will go back to the another problem where we will have to use conservation of mechanical energy, and then conservation of mechanical energy with losses. So I still have 3 problems prepared. But again, if you feel like you're getting too tired, you can, of course, go. Okay, any questions? Okay, busy. Good, guys? Following? Okay, good. Yeah?
Do you technically solve that with kinematics?
With what?
Kinematics.
No. Kinematics, it's only about motion, where the forces, you kind of ignore forces. You just assume that there are initial conditions. And here we have some initial conditions, but every time it's a system is still under the influence of forces. We cannot just solve it with kinematics only, right? So every time we assume that no more forces acting on this. No, there are forces, but
I mean, I was just curious.
no.
You know? All right.
Of course, I started saying that no forces, but of course, in the kinematic equations for projectile motion, every time we were playing with accelerations, right? So not forces, but accelerations, where we assume that we know that there's acceleration g in a certain direction, right? So, but these problems, no. Although I never tried, and now I need to, you triggered the process, so it started boiling in my head somewhere. Right. Okay, anything else? Okay, then let me start erasing this. And so that was 4, now 5 will be. Every exam review session I start complaining at some point, because yeah, it's for a couple of days my shoulder hurts erasing all this, and it's sometimes not that easy to erase. You know what, let me just quickly check. Oh, yeah. Okay, it's recording. Good. Okay, I just prepared this problem like 40 minutes before the exam review session. So, situation. Okay, let me first write it's number 5, and it will be about power. So, it's the same, I mean, we're going to solve this problem using both approach, using average power and using instantaneous power. Because if the force is constant, you can solve the same problem using this, and the answer will be the same. It's like if you want to find, let's say, velocity constant, it doesn't matter which method you use, you can find, if you use instantaneous expression for instantaneous velocity or average velocity, if velocity is constant, it will be the same. Right? So the same situation here. So there's a box on the surface with friction, and we want to drag it with some motor, which is somewhere grounded, attached to some, and cord connected to the motor and connected to the box. And so we want to drag it. And coefficient of kinetic friction is given. So we need to find how much of power must the motor provide in order to move that box with, again, constant velocity. Every time, whenever, as I keep saying, whenever we drag something, push something, we try to do it with the constant velocity. So, but we want to move it with the speed of 0.5 meters per second. So how much of power must that motor supply in order to drag it with the velocity of 0.5 meters per second? So this is the situation. So let me write something. So we have a box slash motor, and on a surface with friction. Okay, as usual, I will start with a picture, and then once I introduce something, I will write down what's the value. Okay, so this is the surface. Immediately, x-axis. Then let me draw the box here, heavy box. Mass is 300 kilograms. Okay, so let me write M of the box, 300 kg. So I don't know how to draw the motor. Sorry, guys. Okay, let me draw some cylinder, grounded, and some cord attached to the. Okay, modern art. I'm not trying to sell it for millions like Malevich did for his black square. All right. So then, yeah, let me even still explain modern art with explanations. Right. So that's x, maybe over here somewhere y-axis, right? And yeah, we want to drag it with a constant velocity. So velocity of this box, v, and let me write the value, is 0.5 meters per second. Okay, let me write, we want. Maybe after 0.5 meters per second, the box will start falling apart. Who knows? Or like when I used to work at the Institute for Single Crystals in Ukraine, and we used to drag the crucible with some aluminum oxide. And you need to drag it with a certain speed, because if you increase that speed, then bubbles start getting into the crystal. So there's some every time critical velocity. If you exceed that velocity, then the front of the during the crystallization will not be able to push the gases. Right. One of the examples. So anyway, there are different situations. Why 0.5? Okay. And what we need to, yeah, we need to find the power, as I said. So we need to, I think I gave you, coefficient of kinetic friction. Mu k equals to 0.6. And so what we need to find, power of the motor. So in order to achieve these parameters, the motor must have a certain power, must be able to provide a certain amount of power. Right. So first, I want to use, let's first use instantaneous power. Let me call it, I don't know, part A. Let's use an instantaneous power. Because obviously in this case, force will be constant that the motor is going to provide. Yeah. So I want to use instantaneous power. And so instantaneous power, you see, it's a dot product between the force and velocity. So P equals to F of the motor dotted with the velocity of the box. So immediately, you see what needs to be found? First of all, force of the motor. And in this case, it will be which force acting on the object? So the motor will do something, right? So turn something, and then through which object that force will be applied on the box? This is the cord, or whatever. Of course, tension of the cord. Essentially, the force of the motor will be equal to the tension of the cord. Yeah. Okay, so obviously we need to analyze forces. Let me draw free body diagram. Let me show all the forces acting on the box. So this will be Ft, which is equal to F motor tension, right? Then, of course, there will be weight, mg. Then there will be normal force, Fn. And what else acts on the system? Okay, surface with friction. So since velocity that way, so there must be friction. Kinetic friction is in the opposite direction. So let me show it. So F kinetic. Okay, free body diagram, coordinate system is given, x, y, so we all set. Now we need to find the value of the motor force. Again, Newton's second law, still like a couple of problems ago, we started with, in order to find the value of the force, we started with Newton's second law. Right, okay, so, okay, let me raise the question. So we need to find F motor, right, so first. So sum of the forces in the y direction equals mass times acceleration. Sum of the forces in the x direction equals mass times acceleration. In the y direction, acceleration is 0, right? Because again, object is not jumping, is not doing anything weird. So then, acceleration in the x direction, everything is staring at you, is looking at you. They're smiling. It's not that obvious. Yeah, acceleration is 0 because again, as I keep saying that whenever we drag something or push something in practical, in real world, we do it with constant speed, right? So, of course, acceleration is Ix is also 0, v equals constant. Okay, and in this case, equation in the y direction, is it important in this case? Come on. In equation in the y direction, it will allow us to find what? Yeah, I agree. Because friction is in the game. So if there is a friction, of course, we need to start usually, not need to, but it's better to start with equation in the y direction. Right? Yeah, oops. All right, so of course, from this equation, we can get immediately that the normal force equals to mg. Right? Of course, we knew it. I could have used it immediately without even explanations because it's our recent past. And as a result, we can find the value of the kinetic friction force. Right? Mu times, okay, mu k times the, you know what, I feel like it's in my way. I need more space. So let me erase it while you're still writing. During the classes, I try to keep all the written stuff on the whiteboard so that I can compare things in different problems. But in this case, we have too many problems. Okay, good enough. So, kinetic friction, it's a mu k times the value of the normal force. So it's a mu k mg, mu mg. Good? So, okay, now x equation. Again, it's your previous midterm exam, so I'm not asking much of questions about this. In the x direction, tension, positive x direction, friction, negative x direction. So So it's a Ft minus Fk equals to 0. So from here, of course, tension equals to the friction force. It's like in the first problem when a person applied force in order to move the piano down the incline with the constant velocity. You remember the force of the person must be equal to that component of the gravitational force. Here, the motor must balance that force. So immediately I can rewrite it over here. So it's a mu k times mg. Okay, so now we know, and of course it's a force that the motor has to apply. Right. So we found this. So now we can find what can be found now? The work. Oh, no. We found this. No, nothing needs to be found. So now we just need to take a dot product of the velocity and this force. So now back to our power. So P equals to, again, let me rewrite that F of the motor dotted with V. Again, dot product by definition, magnitude times cosine of the angle between these two vectors. So it's F motor times, okay, let me just even remove V and cosine of the angle. Which angle? No, look at the picture. So this is the force of the motor. You see the force of the motor? Yeah. Right. Then velocity, you see?
Oh, 0.
Of course, 0. Right. Again, that's why picture is very important, because if you don't draw it, you can, it's this, and then later on, kind of, oh my God, how could I make a mistake like this? It's absolutely silly. Right. So, although I feel kind of confident, and still I prefer usually to draw the picture to make sure that I don't make any. We're still humans. We're humans, right? We can make any silly mistakes. It's 0 degrees. Actually, everyone sees 0 degrees, right? Because again, two vectors in the same direction, velocity and the force, tension force, which is the motor force. Right, okay, so we get motor, it's mu k mg, just mu k mg, and velocity, right. Okay, mg v. Okay, let me compare, because it's absolutely new problem. I just created like just before the exam review session. Yeah, mgv. Again, you can plug all the numbers are given, and so I will write down the answer. 882. Units, usually students remember units of power, because we use it in everyday life quite often, right? So. Yeah, you know, we lamps, bulbs, right? So whenever you go to the store, you can look at the bulb. Of course, watts. Everyone knows. Of course, yeah. You just need to realize that most of the, most of the time, you know answers to most of my questions. Just not realizing, right? So of course, watts. Or if you don't remember, at least write down all the units which you see in the formula. Right. Okay. So it's one way. Yeah. I never used that. Of course, when I was a student, maybe once or twice I used horsepower, but I'm not a big fan. So whenever I see it, I kind of, it's not a, actually, I don't know if, probably it's not SI units, those horsepowers or donkey powers, whatever. So I even don't remember the conversion between those two, because I barely used it. Yeah, alternative. Okay, another way. Again, as I said, this formula is true. You can find, even if the force is changing from point to point, from moment to moment. So, of course, in this case, power will be different. So you just, at this moment, force is, 5 newtons. Velocity is 3 meters per second, so 5 times 315. Next moment, 6 newtons and 2 meters per second. 6 times 2, it's a 12, right? So it's a different number. So it's an instantaneous power. So pretty much you can find power at any moment of time. But if the force is constant, then it doesn't matter if you use average value of the power, expression for the average power, or instantaneous power, the answer must be the same. So let's just apply now this expression for the average power, because the force that the motor applies is constant. Okay, so let's another way of getting P. But now the average power. So the average power, and you see bar on top. Whenever bar on top, it's usually, most of the time average, or sometimes these triangular brackets can be used. So P, I drew it as a vector, sorry, force of habit. So P bar equals to work divided by the time over which that work is done. And the work done by which force? Motor, right? Motor, right? So it's a work done by the motor divided by the time over which that work was done. Because the total work, as you said in the first problem, right? So the total work, you remember what is the total work over here in this problem? 0. Because again, we move this object with a constant speed. Whenever you see system moves with a constant speed, you can immediately bet all your money that the total work is 0. Right? Although I wouldn't do it. Right. Okay, so now we need to find, obviously, work done. Time is not given, but we'll see what can be done about that. So force we found. So work done by the motor. Of course, it will be force done by force applied by the motor dotted with the displacement. Back to this, right? Okay. So force of the motor, it's okay. We found. No, let me write underneath. So F motor, then D and time cosine of the angle. And the angle, what's the value of the angle? You see? Between force and D, force that way, D that way also, displacement. Yeah, 0 degrees, of course. Yeah, good. 0 degrees. So value of the, okay, you know what? I'm not going to plug the expression for the force. I will just use it, write it as a force. So it's a force. Okay, you know what? It's ugly. And now this expression I can, because again, displacement is not given. So let me plug it. So the average power will be equal to, so it's a force of the motor times D and divided by the time. And D over time, what is D over time? It's a velocity. It's velocity. And in our case, since object moves with a constant speed, so yeah, instantaneous velocity, average velocity, it doesn't matter. Right? So, yeah. F motor times V. Essentially, we derive the formula for the instantaneous. So pretty much now, again, we have everything that is given in order to solve it, even using this method. So it's a mu k mg times V. So the same, over there, the same, m mu k mg V, the same. Because again, force is constant. If the force were different, or velocity would change from point to point, then of course this would not give us the correct result. It would actually give us an average, truly average. Right. Again, application of the power, it's reasonably easy, just a preparation. You need to analyze very quickly forces. And again, after all your experience which you had preparing for the second midterm exam, this shouldn't take much time. Yeah.
What does that say?
the same. And this is a happy face, of course. All right. You know what? Anything else? Yeah.
This is unrelated, but I'm gonna go soon. I was just wondering where the recording would be uploaded.
I need to prepare another exam for my second section, right? So, but anyway, I will try to finish it today if everything is fine, right? So, usually by tomorrow morning, it's the best because usually it takes a couple of hours to put it together, then rendering. Premiere Pro, Adobe Premiere Pro, it takes like a couple of hours because the video is long. And then even just uploading to YouTube, and it's another couple of hours, right? Yeah, usually I upload on YouTube.
Would it be like a public video?
Yeah, it's a public. All my videos are public on my YouTube channel. Right? Just type in YouTube my first name, last name, and it will pop up, right? So, right. And I'm not monetizing it, so it's just. Plus, it's not powerful in order to apply for monetization, and plus, I don't do it right. I just started it during the lockdown because sometimes connection is good during the live classes. Sometimes connection was not good, so as a result, I would immediately after the class I would upload everything, and it was useful, very useful. All right. Okay. So now, you know what? Because yes, some of you need to go. Let me solve the problem about a system where there are losses. And then if you still feel like we can go back and solve another problem where there is no losses of energy. All right. So any other questions? Yeah.
Power's going to be on like our exam on Wednesday for your classes?
Say it again?
Is power going to be on the exam on Wednesday?
Yes. Power will be definitely, right? So I know in many sections they actually also conservation of linear momentum is already on the exam, right?
Yeah.
So, All right, so where we are, so it's a new, okay, yeah, this is, okay, let me erase. I think this should be enough space to solve another problem. Okay, some complicated shape of a truck for an object. So that was 6, now 7. Let me put number 7. So is it, okay, some block on a, okay, some track. Okay, let me draw. It's much easier to draw than explain what actually happens with the system. So there are two on the ends, two circular shape pieces of track. So let me do it this way. So over here, the first quarter of a circle. Then there will be a horizontal part. And then there will be another, wait. This way, yes. Right. So this is a rough surface. Let me draw it like this. So there is a friction. Here, no friction. Here, also no friction. Right, so let me maybe even write over here, no friction. Here also, no friction. Then this height is given. Okay, now some parameters I need to add, and let me use different color. Again, this is the quarter of the circle. So this is vertical. So this height, okay, and is L. I think it's L capital, right? Yeah, L capital. Then box of mass m, but it's not given. Actually, no even numbers. So we have that block. For now, let's say it's m. We'll see if we need it or not. L is definitely given. So this is given. But if we feel like we need to introduce a certain parameters in order to go through the solution smoothly, introduce them. Most likely later on they will disappear. So then, coefficient of kinetic friction is given. Yeah. So over here there is a friction. All right. So with friction, and the coefficient of kinetic friction is given, and that is 0.08 over here, only at the bottom. So then our object is I think it's released. Yeah, released. So let's say over here we have some object. You know what? I drew it as the circle. You might confuse. Maybe you start thinking that it can roll. No, it's just slide. It's slides, right? So this is our M. So let me draw it as a box, small box. So only sliding. So M is released. And let me call this as initial point. So this is initial point. So released, of course, from the initial point. So now, of course, it will start accelerating, comes to this point, right? So having some non-zero velocity, then it will start slowing down, friction. And then, of course, most likely, maybe it will still have some amount of energy left, and it will climb up. So we need to find the height where the box will stop. Right. Okay, so that's the problem. So now this will be some final position. We don't know where it is, so I will just introduce as my unknown. And I think I label it as h. So this h is our unknown. So this is h, which needs to be found. So we need to find that h. And of course, at this point, it stops for a moment. And of course, then it would start sliding back. So it stops. It stops. So final velocity, of course, will be 0. OK, so let's start analyzing. I think I gave everything. Let me again check. L and the coefficient given. There is nothing else. Yeah. So analyze forces in order to, of course, if you don't want to analyze forces, I don't know, just grab this and you can use it. It doesn't matter which forces are present in the system. Conservative, non-conservative, this principle doesn't care. Just calculate all the works and you will end up with the correct answer. But since we're trying to make our life a little bit easier, so we derived these formulas. So gravitational force, conservative force, we can introduce potential energy, mgy. Spring, there is no spring, good. Then, what else? Normal force. Normal force, it's a force of constraints. It doesn't change the state of the motion. It's all the time perpendicular to the motion. It just guarantees that it moves along a certain trajectory, a certain path. Right. So again, it doesn't do any work, so normal force doesn't play our energy game. We can forget it. And then we have a friction, non-conservative force, so which will give us some losses of energy. So it means that we cannot use this. So energy actually is not, mechanical energy is not conserved. Some of the mechanical energy will be transformed into the heat in this part, right? So because of the friction, so there will be some heat, right? So thermal energy. So mechanical energy will be transformed into some thermal energy. Okay, so it means that, yeah, this. So there are losses, there is a non-conservative force, so we will have to calculate work done by the non-conservative force. Okay, so now, since there is friction force. So which give us losses. So we need to use that formula. So E final equals to E initial plus work done. Okay, you know what? I can do better than this. W plus work done by the, in this case, friction force. And again, this, although we wrote plus, but every time this force, this work is negative, because every time friction force is in the direction opposite to the direction of the displacement, right? So every time that will be negative. Okay, so that's our equation for this problem. So we just need to apply it properly for this particular situation. Right? And of course, we need to make a decision which point is initial, which point is final, and in this case, it's obvious. This is the initial point, and that will be our final point. Of course, if you don't feel confident, you can split this. First, find velocity over here, then find velocity over here. Then it's too tedious, right? So it's better to just start initial point, final point. Right. So this will be final point. Right. So let's start writing explicitly. So E final. So it's a kinetic energy of the object at the final point plus gravitational potential energy at the final point, like what we did, okay, in the problems which I erased already. Then initial total mechanical energy at the initial point. Again, K initial plus U gravitational initial, and the work done by the friction force. Okay. Again, usually next step, I start ditching all the quantities which are zero. So, any zero quantities? Yeah, kinetic energy at the initial. Because it is released, so initial velocity is zero, so this can be ditched, so 0. Then, what else? Final kinetic energy, the same. It's a turning point, essentially. It's a turning point, right? So it stops for a moment, turns around, and then, of course, it will start sliding down. But that's not our. We're not interested in that. So again, V final equals 0. It stops. Then, I forgot to bug you, and that guy already left. So we playing with gravitational potential energy. We need to make a decision where is our reference level. Again, it's up to you where to position. At this level, that level, but I think the most convenient level, of course, is at the bottom. I doubt that you would disagree with me. So let me so UG equals 0. That's our reference level at the bottom. And as a result, because of that, actually, where did I pick? Oh, yeah, I picked at that level. Just checking my notes. All right, so none of the potential energies are 0. If we picked over there, this potential energy would be 0, and this would be negative. But then it will be L minus H will be involved. I don't think it's a simplification, so let's just keep it this level. At this level. Okay, let me write, and then I will start taking care of the work done by the friction force. Final point. Positive because it's above the reference level, so it's mgh, this h. And positive because it's above the reference level. So again, let me put plus mgh, and h is our unknown, right? You remember. Then initial mg, and what is the height for the initial point? Okay, Linda, you were busy. Right? So, what is the height of the box above the reference level at the initial point? Hmm? L. L, of course, yeah. That's what you want to say. Yeah. So mgl, and again, positive. And work done by the friction force. Okay, so now we have to leave this point. We will come back to this expression. And first of all, we need to find friction force expression. And only then we will start calculating the work done by the friction source. So friction force. So first we need to find Fk in order to start playing with that work. Right. And again, Newton's second law must be still applied. Right. So you know what? Let me I should draw. Yeah, let me draw the box over here when it's there. And all the forces. I should have done it probably at the very beginning. Normal force, Fn, which again doesn't play the energy game, but it's still there. Force of constraints. Then, of course, mg, straight down. Then displacement that way, velocity that way. Maybe let me show that. Of course, velocity this way. And the friction force will be, of course, in the opposite direction. So this will be Fk, right? Kinetic friction. Again, it's exam number 2. And again, y equation in this case will be useful, but we know the answer. Okay, anyway, so let me write very quickly. Sum of the forces in the y direction equals mass times acceleration in the y direction. Acceleration is 0, and from here we will get the normal force equals to mg. If you write it immediately on the exam, of course I will buy it. At this point it's trivial. And then acceleration, Newton's second law in the x direction equals mass. Actually, we don't need this x. In this case, actually, Newton's second law in the x direction is not actually needed. Because what we need to find? We need to find the friction force. Now we know the normal force, just multiply it by the coefficient of kinetic friction, and that will be our friction force. So there is no need in the x equation in the x direction. So F kinetic equals to mu times Fn. So it's mu k times mg. And I'm probably also getting tired. So okay, so now we have this friction force. So now let's find the work done by this force. Again, everyone follows. Again, right now we're doing stuff from the past. Okay, so work done by the friction force, it will be kinetic friction dotted with the displacement. I think something, okay, additional piece of information I missed, right? So I was looking at my notes, and only now when we came to the point where I have to use it, right? What I didn't give. Yeah. The problem says that displacement equals to this L. Right. Yeah. Yeah, sorry. Right. So this is also L. Okay, it's a little bit too much of information per square centimeters. High density. All right, L, yeah. Okay, now I realized that something was still missing. Okay, so again, it's a Fk times, okay, not L, not D, now it's L, sorry. And now, which angle? Now back to like what we started the exam review session. So what's the angle between the kinetic friction and the displacement? Kinetic friction, yeah, absolutely correct. So kinetic friction that way, displacement that way. You know what? Probably I should have showed as a vector. This is our displacement, right? So, and of course the value of the displacement is L, magnitude. Yeah, 180 degrees, right? Good, good, good. So now I see that you got it. So cosine of 180 degrees. And that cosine, of course, is going to give us a negative work, as it should be, because the friction force every time does the negative work. It's just dumps energy out of the system into the outside world. You remember, as I keep telling you, the work plays the role as like, it's like a bridge between the energy of the system and the energy of the outside world. If the work is positive, so energy from the outside world is dumped into the system. If the work is negative, energy is taken away from the system. Right? So will be minus Fk times L, right? And it is equal minus Fk, it's mu mg times L. Okay, almost done. So now we need to go back to our equation which we abandoned over here. Right, so let me maybe highlight it so that, right, so back to our equation. So now back to our equation. So now let me rewrite it over here. Let me even maybe show it like this. So again, mgh equals to mgl and plus the work done by the friction force, which is minus mu k mgl. So minus mu k mg times L. Whew. Again, mass distraction. Mass can be cancelled. And h is our unknown, right? So this is h is our unknown, the only one, because L is given. Okay, g is also g can be cancelled. I love this problem. Right, so g can be cancelled. Right. As a result, actually, we don't need to even to solve it. It's already solved. We just need to rewrite expression for h. So h equals to, I can factor out L immediately. So it will be L1 minus mu k. Nice, simple expression at the end. You can plug any L, and you can get immediately. And mu is given, so it will be 0.92. 0.92 times L. So this will be the height. Not much of a losses, you see. Here it was at L, this height. Here it's a 0.9 L. Some small losses, so it's not much of a friction at the bottom. Yeah, coefficient of kinetic friction is not large. Okay, done with this. Yeah. Okay, it's a little bit more complicated, right? So in the past, a couple of times we used this problem, and whenever we give a problem about system with losses, work done by the friction force, usually it's a huge, huge problem for lots of students, right? So we kind of try to be careful with the friction force. Okay, so I prepared another problem. I don't know if should we discuss it or not. Okay, let me describe the situation. Oi, I even brought a special prop. So there is some ball attached to the string, right? Length is given L, right? And then you just release it. Of course, the point of contact is hold the same place. Of course, it will go down. So we need to find velocity at the bottom. Okay, not the bottom, at the lowest point, right? And then at this point, okay, it's the first part. We need to find velocity over there. Then at this point, there is some peg over here, some nail, whatever it's so. And as a result, of course, this mass is going to start spinning around that peg. So we need to find, I think, something velocity, final velocity at the top of that small circle. So essentially, this situation. Okay, I feel like I need more hands. But you got the point, right? So, or I can use this. Okay, not enough velocity, right? But it's supposed to go to this maximum point, right? So we need to find a velocity at that top of that small circle, right? Okay, should we solve it? Or, yeah? Wow, so. Okay, good. All right. Because yeah, I see you're all getting tired, right? And yeah, power we don't need. So that was 5 and then 7. I miscounted.
Yeah.
Oh my God. Okay, yeah, we're all getting tired. But of course, sooner or later I'll spot it. So that was 6. Now 7. And again, I think this problem was offered by the previous instructor, maybe like 10 years ago on the exam. Again, from the point of view of solution, it's similar to what we did over here, just geometry is slightly more complicated, that's it. Right. Actually, I would say it's even somewhat interesting geometry. So we have a, now it's number 7, so we have a ball on a, what, cord or string, no, cord, okay. Slash, okay, let's say we add also, there is a peg somewhere, which give us a smaller circle. Again, as usual, from the picture, because then it's easier to explain what is given. So the point from which the cord is attached. So here we have, let me make it longer. So this is the cord, L. So given, again, no numbers. So L is given. Then what else? Mass, actually mass will disappear, so mass is not given. But again, we can introduce it. And then something else I will show later. So this is the ball. So then it will go, of course, around this circle. So this will be lowest point. Right. And at this point, we need to find velocity. So this will have some velocity. Let me call it V2. Okay, I will label. This point will be my point 1. This will be my point 2. Wrong color. So this is position 1. This is position 2. And then position 3 will be, of course, the final point. So then, it's for part A. Then over here, there is a peg. So let me position it like this. So it's a peg. And it's right below the point of contact. Right, so at the distance 0.8 L. So this H, let me label it somehow like this. So this H, let me write it here. H equals to 0.8 L. So position of the peg relative to the point of contact. So then in part B, of course, this cord will start spinning over the smaller radius. Right. Okay, not perfect radius, but something like this. Right. And we need to find velocity at this point. So this will be our point 3. Will be point 3. And we need to find, and now this is in my way. Okay, I will rewrite it. So we need to find velocity at that point. So we need to find velocity at point 3, V3. Circular motion, tangential velocity, essentially, in this case, right? Tangential velocity. Right? And, okay, this distance, let me show it over here. It's H equals to 0.8 L. So now everything is given. So we need to find those two velocities. Okay, let me stay hydrated. So yeah, it's released. So of course, initial velocity V1 equals to 0. V1 equals to 0. Again, it's important. Right? Yeah. Okay, so let's start discussing. what can be applied? Again, even without discussion, just work kinetic energy and start using it. But we try to use these tools which are supposed to make our life a little bit easier. Right? So again, force of gravity, conservative, great. Then no air resistance, assume that's negligibly small. And no any frictions anywhere, so everything is nice. So reasonable assumptions. It means that mechanical energy is conserved. We can use conservation of mechanical energy.
Is there no like tension in the core?
There will be tension, but tension in the core. What's the work done by the tension? You remember there was a clicker question in our class. You remember I was spinning this, exactly this.
Not like it's taut, so there's like no slack in it?
No. Look, of course, in this case, displacement, in order to discuss the situation, you need to discuss infinitesimally small displacement. Okay, at this point, infinitesimally small displacement, what's the direction? Tangent. You see, okay, this I'm using it. And the direction of the force?
Be along the core.
Yeah, along the chord, of course. Yeah, along the chord. So what's the angle between the displacement, infinitesimal small displacement, and the force? 90 degrees. Cosine of 90 degrees? 0. No work done. Again, in this case, tension, again, it's a force of constraints, essentially. It just give us circular motion. It's like in this situation, normal force, it's a force of constraint. It just guarantee that object is moving along a certain trajectory, but since it's every time perpendicular, it cannot change the state of motion. It cannot accelerate, it cannot decelerate, it cannot do anything except for stay along this, along this path. Okay. So in this case, tension, it's a force of constraints. It doesn't play the energy games all the time. Right? So we can kind of ignore them. Right? Okay, not ignore, justify, after justifying. Right? Yeah. Not cancels out 0. Work done is 0, right? Not cancel. Right. Okay, but actually good. I forgot about tension force. It's I should have mentioned it. So as a result, yeah, conservation of mechanical energy can be legitimately used over here, right? So yeah. Actually, let me still mention about the tension. So work done by the tension force equals to 0. So again, it doesn't play the energy game. You know what? I feel like my marker is getting losing contrast, so let me change it. So we can start writing. So part A, total mechanical energy at the, okay, it's a point 1, not initial. Let me use level 1, okay, not point 1, equals to the total mechanical energy at point 2. Because in the first part, we need to find V2. Let me actually write. So we need to find V2 in part A. Right? So again, let's write explicitly. So the kinetic energy plus potential K1 plus U gravitational 1 equals to K2 plus U gravitational 2. Again, what's the reference level? Where the reference level? Again, it's up to you, but of course you agree that the most convenient is at the lowest point because all the potential energies are going to be positive. But if you position it over here and over there, it will be also correct. But in that case, some potential energies will be negative, right? Okay, so let's make them positive, following the advices of psychologists: be positive, be on positive side, think positively, and whatever, blah blah blah. Right? Okay. So U gravitational equals to 0. That's our reference level. Right. Okay. Initial kinetic energy? 0. Of course, it is released, so 0. Then final gravitational potential energy. It's a reference level. UG2, it's at this level. It's our reference level. Potential energy is negative, right? So also 0. Nice. One term and one term on both sides. Great. All right. So nothing else needs to be done. We just need to write it explicitly. So gravitational, it's above the reference level, so it's positive. mg. And which height? Can you see what is the height above the reference level in order for me to write the potential energy of this point? No, 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 no. 0.08 L, it's at this distance to the peg. Simple geometry, right? Yeah, I see the guy is blocking your field of view. Okay, it's a circle. So the length of the chord is L. So when it comes to the bottom, so what's the distance between this level and the bottom level? L here. Of course, it's a L everywhere. It's a circle, the simplest possible figure, right? So of course L. Of course L. Yeah. It's at the very beginning. Not every student see that, so that's why I started bugging you. Right. So of course L. Right? Yeah. Good. All right. So this is maybe let me even show to emphasize on that. So of course this distance is L also. Wait, L small, not L capital. It's a L, this L. Right. I just, with that problem we use L capital, so of course my brain now starts information overlapping. So mg, L, and of course positive because it's above the reference level. Okay, great. So then on the right-hand side, it's just a kinetic energy with our unknown. So 1/2 mv2 squared. Again, masses can be cancelled. I guess mass distraction. Right, so m, and we can get the velocity. Right. So v2 equals to square root of 2gl. Okay, first part is solved. L is not given. I mean, it's given, but no numbers. So we just leave it in this form. So part B. Oh, maybe I should be able to finish it using this. You know what? No, I want to erase this power problem. So part B. So now we need to find velocity at point 3. Again, keep using conservation of mechanical energy. We justified that it's applicable over here, so now we can use it between any 2 points. So now our unknown is at point 3. Of course, E3 must be equal to whatever initial point you want to use. It's your call. You can use E1. You can use E2. I prefer to use E2, although I think E1 will be also great. So, but I think in my notes I used E2, yeah. Because we know everything about point 1, about point 2. I mean, information about all parameters, right? So now, like here, and now let's start writing down everything explicitly. And then we will see what needs to be found. So first, let's write down all the terms, and then we'll start finding if something is not given. Okay, K3, that's an ugly 3, plus U gravitational 3 equals to K2 plus U gravitational 2. Again, gravitational 2, I mean U2 we discussed in the previous, so this is 0. Then on this side nothing is 0, right? Kinetic energy, it might be 0, but we need to calculate that. It will be special case. Gravitational potential energy at point 3 is not 0 because it's above the reference level, right? So pretty much that's it. So now we need to deal with those 3 terms. And so K3, it will be, let me continue writing in order to see what needs to be found. V3 squared, then plus mg, and now we need to find this Y3. And that is not given, so we need to find it. Yeah.
Would it not be like L minus?
Yeah, we need to do some calculations. So right now you did it in your head very quickly, but we need to show it. Right? So, but anyway, we need to find Y3, which is this. Right. It's not given, but we should be able to find it because geometry, enough of geometry is given. So, and equals to 1 over 2 mv2 squared, and we know v2. It's from the previous part. So yeah, we're all set. We just need to find y3 because right now we have two unknowns, this and that, which is not good. So we need to find y3, and then we should be able to find velocity. Okay. Okay, so this is our global unknown, and this is our local unknown, which needs to be found in order to use, in order to finish using this equation. Right? So now let me write this local unknown, local goal. Right. So you know what? Let me label these points. Essentially, we need to play with these distances, right? So let me label. I know this point is A. This point is B, this point is C, and this is D. And so we need to find BD, essentially. It's a BD. Right. Okay. This distance AD, we discussed with you. Okay, she's busy. AD. It's a L, right? So AD is L. Then the distance to the peg is 0.8 L. So we should be able to find this. CD, it will be L minus 0.8 L. So this distance will be 0.2 L. Okay, let me just write that down quickly. Okay, let me erase this. So CD equals to A. Ooh, that's an ugly A. AD, it's almost like my initials, AD, right? So AD minus AC. Yeah, AC. Oh, it looks something familiar. And AD, as you said, it's L. It's the total length of the chord from A to D. And from A to C, it's your first option for the distance. It's a distance to the peg, which is 0.8 minus 0.8 L. So, of course, 0.8 L, 0.2 L. So essentially, it's the radius of this small circle, right? It's a radius of that small circle. So, and we need to find y3, which is essentially diameter of that small circle. So just multiply it by 2, that will be y3. See that? So it's a diameter, essentially. Yeah, great. Right, so now our y3, which is BD, it's a 2 times CD, right? So it's a 2 times 0.2 L. So it's a 0.4 L. So that's the height to the 0.3 from 0.2. Okay, so now we found this, and we should be able just to plug it into our expression and finish the problem. Right. So now let me continue this line below. Okay, I will just continue rewriting 1 over 2 mv3 squared plus 0.4 mgl. I just plug y3, right? 0.4 mgl. And equals to, okay, v2 we know. Actually, did I plug this 2gl? Let me just look. Yeah, actually I did plug. But I will do it later. So I will just treat v2 as being given, equals to 1 over 2 mv2 squared. Again, mass goes. Mass destruction, right? So, and v3 is our unknown, right? So again, I will multiply the whole equation by 2, right? So it will be v3 equals to square root of these 2 will gone, v2 squared and minus 0.8 gl. Okay, this time I made one step. I just basically multiplied the whole equation by 2, move this term to that side with minus, so it will be minus And since I multiply the whole equation by 2, so 0.4 gets transformed into 0.8. Right. Again, just simple manipulation, algebraic, so you should be able to follow it. Right. Okay, and now let me plug 2GL instead of V2. Followed? You understood how I move from here to there? Yeah, good, good. So 2GL, right? This box, it's my explanation box for those who are not in my recitation classes. I usually write in this like a parenthesis explanation box to show what I'm planning to do to move from this equal to the next line, I mean to the next point in the line. Right. So over here, I'm just planning to use V2, the expression for V2. Right. Again, when I was a student, my professors used that, and I loved it, and I still use it. I still use it. So 2GL minus 0.8 GL. Right. Because we're squaring, so that square root disappears. So 1.2 GL. And let me compare. Yeah, 1.2 GL. Done. Again, numbers are not given. So everything is in terms of L.